7th week of Edinburgh University Young Scientific Researchers Association, or EUYSRA for short. Before we really get started, I'm just going to give you a quick rundown of what we'll be doing tonight. And it'll be me, for the benefit of the esteemed academics that we've invited, the schools that we've invited, and the non-members, that I'll be giving a quick introduction to what we are, what we hope to accomplish, and what we have accomplished. Then, in the continuation of our speaker series, we have an audience with Peter Higgs, which I'm guessing everyone knows. And then, as this panel, we have 4 esteemed physicists. We have Alan Walker, Peter Higgs, Victoria Martin, and Francisca Garay. Is that correct? Garay. And then we will continue with our trademark debate in the end, or presentation, Principia Scientifica, where a topic is chosen the week before, and then we have 2 debaters or presenters who will argue one side of the argument, either for or against. And this week we have, can scientific theory ever be considered undeniably true? And last week's winner, Kitaki will be debating against David Pemberty, a former champion of the society. So, most of us, are university students at this university. Some of you may be considering to apply here. Some of you are academics at the university. It's a university which is very known for the research that is being carried out and has been carried out in the past. We're a member of the Russell Group, an elite research group of, 24 universities in the UK that receive more than 67% of all research grants within the United Kingdom. On a European scale, we're also a member of the European League of Research Universities. So there's no doubt that the expertise, the manpower, and the labs and the equipment and the funding is at this university. But the vast majority of us are undergraduates, or in the case of the students from the schools, to be undergraduates. And where does that leave us? Well, everyone here has applied to a certain course, a course that you'll be doing for the next 4 or 5 years, all depending on what it is. So in these courses, we all know it to be true that it's being completely dictated to us. The path that we take, everything that we do, has been set for us. So there's little room, although some courses do try, for getting the students to become innovative and having novel ideas or approaches to projects. But we find that the best way to really kick off student innovation is when peers work together, when we teach each other, when we learn from each other, and where we just work in teams. So this is how it's broken down. We've set it up in 7 departments, all being headed by 1 or 2 people in the case of medicine. And then here, people will gather on a weekly basis to discuss what potential research they would like to carry out. The whole point of the aspect is for teamwork and brainstorming. And we all know that scientists are stereotypically classified as shy individuals. So what we hope to accomplish by having these weekly meetings where people get to vocalize their ideas, you become confident in what you believe in your convictions. So we want you to take the chance to articulate what you believe in. Then of course, there is some standardization that we have introduced to the society. We have a format, a research template, which we have dictated to you, where you will write a small proposal of what you hope to achieve, who will be involved, how much it will cost, how long it will take. And then you will present this, again, for the sake of getting you out of your comfort zone. For you to learn to speak to a larger crowd, you're presenting to a research panel, which includes Jan Silkovsky, Nawi Shahid, me, and Vijay Gadia. And Vijay, he's an accountant, so our money's in safe hands. And then what we try to establish here as well is, as you can clearly see, we're students. So we do not know everything, and we cannot claim to know everything. So what we do is, we invite 2 academics from the university to come sit in at these research proposals. And it will usually be a PhD from the respective school and an academic from the respective school. And then they will advise us on how to invest, on how to carry out the projects, all depending on what they think would be better for the process. What we do is then, we've given you the time frame for November the 2nd, which is this Friday. So this is just a timetable for all of you who are involved in the research that will be done, and I'm sure the department heads have informed you of when and where it will be, but just in case you didn't know, it's TV at dining room, and those are the times. And then we will tell you at next week's meeting, which is usually down in Appleton Tower, Lecture Theatre 5, we will inform you which projects we've decided to invest in and which ones we think could use a little tweaking before we go ahead with them. Another thing about being a university student, sorry, I forgot to show you the pictures of what we have done. So once we accept a research project, then we will send you into the fields and we will send you into the labs, all having the academic support and the technical expertise to help us carry out these projects. And towards the end of the project, we hope that you will write a research project, as in compile results, what you learned, what you thought you were going to learn, and what you will carry on to the future. So that's that for the research. But we all know that we're studying something that is making us experts in one specific field. So we are all becoming ignorant to all that is not our own specific field unless we actively pursue information in that. So what we hope to do with these weekly meetings, this bigger one, is where we invite speakers from all across the scientific spectrum. And again, Edinburgh University has an abundance of speakers and researchers. So we started with Luke Bisbee, who told us the importance of doing research and how it's carried out, followed by the innovator and inventor, Professor Harold Haas. Then we had one of the acclaimed producers and inventors, or what should we call him, the cloner of Dolly the sheep, Professor Ian Milwood, followed by Dr. Colin Pullen, who told us about the extremes of chemistry, and then followed by Dr. Bisbee again, who then told us about the misinformation going on in sustainability, followed by Professor Austin Tate, who informed us about the virtual realities and what's going on in that spectrum. So, without further ado, we're all here for one reason, so let me please welcome Alan Walker.
Well, I've been given the inevitable task and an enviable task of introducing what the Higgs boson is to an audience I'm told doesn't know any physics. And that's the assumption I'm going to make. And in fact, I'm going to introduce the background to this by actually tracing out from Maxwell to Higgs the sort of things that actually you need in the ingredients for ending up with such a theory. Maxwell, inspired by the experiments of Faraday at the Royal Institution, came up not with these set of equations, but the equivalent in quaternionic form. These equations are actually due to Heaviside, but it's what we iconically see now as the Maxwell equation. And if you notice in here, we have the magnetic field and the electric field, and the conjecture early in the 19th century was that electric and magnetic fields were manifestations of one and the same thing. Some electromagnetic field, and it's actually with these equations that you can actually show that you actually can get propagating electromagnetic waves, where one of these is the electric field and one of them is the magnetic field, and the wave is propagating in this direction. These electromagnetic waves, when you looked at the constants found in experiments on electricity and magnetism, you get two constants when you put in. And when you actually take 1 over the square root of the product of these constants, what you find is the numerical value of the velocity of these electromagnetic waves equals the measured speed of light. Well, it wasn't particularly accurate if you look at the original treatise on Maxwell, but nevertheless it was extremely convincing. So we actually now understand that light is a form of an electromagnetic wave. And so what we have is a wavelength, and we can actually see two planes, and if this is the electric field vibration, then this horizontal field is the magnetic field direction of vibration. And what we actually discover in this form of the electromagnetic wave is there is nothing that's actually oscillating in the direction of motion. In other words, the electric and magnetic fields are at right angles to the direction in which the field goes. So if we actually imagine that, then the electric and magnetic fields are at right angles to the direction of propagation, and there is nothing in that direction. Now, if we actually look at light, since it can actually be oscillating in that direction or in that direction, and any other direction is a linear combination of those, we see in fact there are two directions in which the electric fields, for example, can actually point, which we call the polarization of the field. So, if I take two pieces of film, these film here, actually this one will only allow light through, which was oscillating in one direction, and this will actually allow it in the same direction, but if I turn it at right angles, will not allow the light in that direction, but will allow the direction this way. So this will actually choose whether it's vibrating in that direction, and that will choose whether it's in that direction. So if this works, hopefully, if you see that there is some tinting of that because there's a certain amount of tint, and the same thing happens here if we put it close. If I now introduce that, you see the light is extinguished. If I put them together, it's much the same, it's a little bit tinted, each one, if I put them with right angles. So what happens is that when the light goes through this one, it's polarized in, let's say, the vertical direction, and this one only allows light polarizing the horizontal direction. Of course, there's none because that's all that's coming out of that one, and therefore if we hold them up, you can see that the light is in fact actually extinguished, but if we actually put them in the same direction, apart from the tinting, it's not. So you can see that if we do that. So we can actually see that therefore light is polarized, and in fact it has what I would call 2 degrees of freedom. Now that's an important thing, because what it actually will show us is that in fact light, if we ratchet forward now into the 20s and 30s onwards, when quantum mechanics comes in, we actually know that although light actually seems to be a continuous distribution of energy, if we look more carefully, what we find is the light is carried rather like a heavy rain, with the droplets of the rains being the quanta of the electromagnetic field, namely the photon. So now we know that in fact the classical field of electric and magnetic field propagating is equivalent to a constant rain of these quantum particles called photons. If we actually go further forward, we actually discover that if we, for example, consider, I've actually got an electron here. We'll come back to the electron in a moment. The electron should be familiar to you. It carries electricity down the wires. I could equally well have an electron up here, but I've chosen to have a positron, which more later. But these are two electrically charged particles, and they will actually bounce off each other in the quantum mechanical way. And what will be exchanged is something that carries the force between them. That's our picture of what happens when we have a force between particles. And it's carried by this photon, and we know that there is actually 2 degrees of freedom for the associated classical wave, vertical or horizontal. So we actually see that the photon here has actually, therefore, must carry either what we call an angular momentum or a polarization, either vertically or horizontally, but nothing in that direction. Now, Maxwell's electromagnetism was also the inspiration for Einstein, who introduced the idea of, let's say, special relativity. He did a lot of other things. And in special relativity, we actually know that anything that's traveling in this direction with a speed close to the speed of light will actually be shortened. It's called Lorentz contraction. And therefore, if light is traveling with the speed of light, that contraction is complete. So that's another way of visualizing that the photon can't have any polarization in the direction of motion. It has to go away. So also the result is if you look at special relativity, this photon here that's exchanged must have 0 mass. It travels with the speed of light, and if you examine relativity correctly, then the only thing that can travel with the speed of light must have 0 mass. So now, the characteristics of this force, this electromagnetic force we can now call it, is it's carried by something which is massless and which has 2 degrees of polarization, or we could actually call them 2 degrees of freedom. Okay, now what's the advantage of that? It turns out that the fact that the force carrier is massless means that the quantum field theory that comes out of this, quantum electrodynamics, in fact, is so accurate in the way we can calculate things that subtle effects in the spectrum, the light emitted by a hydrogen atom, the so-called Land shift, can be calculated theoretically to 1 part in a trillion, and the experiment agrees with that. And if you don't find that amazing achievement of science, then I don't know what will impress you, but maybe there is more to come that will impress you. So this works very well, and essentially, we actually now know that this is an archetypal form of theory called the gauge theory. I won't go into the reason why we call it the gauge theory, it's a long story. And it's actually renormalizability. It means that when you calculate this to all orders, the answers you can get are finite. So when you calculate the charge of the electron, it's finite. You calculate the mass of the electron, it's finite, and so on. So this theory allows you to predict things with increasing accuracy. The only difficulty is when you calculate to many of the higher orders, there's a whole load of calculation needed to be done. But nevertheless, what makes this thing work is the fact that the theory is massless. Okay, so where does the electron come into the story of what we're made of? If you know that the atom is 10 to the minus 10 meters across, in words, that's 10,000 millionth of a meter across, atoms are pretty small. Inside the atoms, and this is not to scale, 100,000 times smaller is the nucleus of the atom, the hard center that carries most of the mass. And our experiments have shown us that inside the nucleus of the atom there are particles called neutrons and protons, and they're not elementary in the sense that they're not made of bits. They are too made of bits, and we now know that, for example, the proton is made of what we call two up quarks and a down quark. They come together in threes, and the neutron, which is neutral, actually has two down quarks and an up quark. Well, that was discovered by so-called deep inelastic experiments, but actually particle experiments colliding has discovered a lot more. And what we now know from experiments done at CERN and elsewhere is that we actually have the electron, which forms the outer parts of the atom. These are the orbiting parts around the atoms that get freed up in metals and carry electricity. We have the up and down quarks that make up our protons. And associated with the electron, there is a rather mysterious and light particle. We thought they were massless at one point, but now know we have a very tiny mass, neutrinos, which actually don't interact very much at all, and neutrinos will pass through the Earth and out the other side. It's been calculated that they will pass through a light year of lead. If you know what a light year is and how heavy lead is, but I don't know where you get a light year's worth of lead, is actually amazing. In fact, relic neutrinos from the Big Bang are passing through your head, so a little known fact is that billions of neutrinos per second are passing through your head. But since they go through the other side of the Earth, you don't form any impediment to their motion. But what we find in nature is there's copies of these things. So if we call this the family of what we now call ordinary matter, ordinary because that's what you're made of and what the whole of the universe is made of, these things are made fleetingly. We have charm and strange and top and bottom. The strange quark is heavier than these, the charm quark is heavier, the bottom is heavier still, and the top is the heaviest of all. And we get a copy of the electron called the muon and the tau and associated neutrinos. But experiments have told us that there are only 3 species of light neutrinos, and therefore this is a picture of what we call the elementary particles of matter. Now these are called fermions because they have the same characteristics as the electron. They have 2 polarization states, 2 forms of angular momentum, but that's a technical matter for us at the moment. And in fact, therefore we have these. Now, it turns out that these up and down quarks don't just come with these, what we call upness, downness, strangeness, charm, and so on, which we call, for want of a better word, flavors. They come in those flavors. But in fact, they also come in color. So there's a red, green, and blue version of each one of the quarks. Why is that important? Well, when the quarks actually interact with each other, they exchange a particle which normally sticks them together in the neutrons and protons. And if it's going to stick them together, what are particle physics going to call them? But other gluons, so the glue sticks these together. But the gluon is the mediator of the force between the quarks. So here's a pair of quark and antiquark going to a top quark and an anti-top quark with an exchange of a gluon. If we actually take a theory where the gluon is massless, and this color, we end up with a theory called quantum chromodynamics. Now it's like quantum electrodynamics. I often used to say that the difference between quantum electrodynamics and quantum chromodynamics is the difference between a black and white TV and a color TV. It's much harder to fix a color TV. And as a result, you can actually see that this is actually much harder to calculate with. Because it turns out that gluons will interact with themselves. The photons don't, but the gluons do. And that makes the theory much more complicated. And in order to calculate processes in what we're going to call quantum chromodynamics, we need supercomputers. And there's a whole branch of our particle physics theorists that do those sort of things. So, again, the theory works in principle because the exchange particles are massless. Now, I described the electromagnetic interaction. The interactions in quantum chromodynamics are what we could call the strong interactions, but there is an interaction in between, and it turns out that the neutron is not stable, particularly if it actually escapes out the nucleus. It will decay with a half-life of about 14 minutes. But in fact, nuclei which are rich in neutrons will actually decay with the, and what will happen is the neutron is slightly heavier than the proton, so we can get the emission of an electron plus an anti-neutrino. Now, if we want to see a picture of this, in the same sort of picture where two particles come in, two particles go out, and there's a force between them, then in fact, if you look at this, what's really happening is a down quark is turning into an up quark, changing from a neutron into a proton, and then since the charge has gone from none to 1 plus 1 here, we have to have a minus 1 coming out, and therefore, in fact, the carrier here has to be negatively charged with the same charge as the electron. The neutrino is neutral, it doesn't have an electric charge. So that's one type of thing. There is actually also electron-positron annihilation, which can give us pairs of what we call bosons, quark and anti-quark pairs, and that's also mediated either by the photon, so it's an electromagnetic interaction, or by the exchange of a particle, which is like the W, but it's actually neutral. Now we know that this force, this weak force, is actually short range, and the characteristics of this is that we would dearly love the W's and the Z's to be massless, but they ain't. The W boson and the Z boson weigh as much as a silver atom. They're a very heavy particle indeed. And in fact, the discovery of these actually leads to a Nobel Prize for Rubia and Antonini. So this is the picture we have of a weak interaction, and these W's are exchanged. As you see, this down quark, these other quarks in the neutron to proton transition are spectators. This one is the one that undergoes the decay, and we get this. So the problem is that this would work beautifully if the particles that were exchanged were massless, but they're not. Okay? So they're not massless, and here's on the scale of what we call giga electron volts, is the photon is massless, but these weigh 80 or 91 in these units. And here are the charges, and the gluon is essentially massless. So what we really want is a way of giving these particles mass, and that's where I hand over to Peter, because he will describe his model, which arises out of work in the 60s and his papers in 64, which leads to the idea of a mechanism that will allow the mass of the W's and Z's. Because if we put the mass of the W's and Z's into the equations by hand, the theory will not work. It breaks down. It is not calculable. It doesn't make predictions you can rely on. So we have to give them mass in a way which actually keeps that underlying nice features or symmetry of them being massless, but gives them mass in such a way as to not destroy them. Peter, do you want to take over from here?
Okay, well, I'm a very low-tech physicist, so I don't use these fancy gadgets. In fact, I don't even know how. So you've probably heard that I've gained notoriety recently as a result of a discovery at CERN, and the discovery at CERN is believed to be of a particle which I drew attention to in 1964, 48 years ago. It's taken 48 long years to get to the point of an apparent discovery. So I'm going to try to tell you a little bit about the story, and in terms of what Alan's been telling you, I'm going back to prehistory. First of all, I should say that the habit of theoreticians inventing elementary particles which are later discovered by experimentalists isn't particularly new. It's almost as old as I am. The first person to do it, I think, was Paul Dirac, who was one of the founding fathers of quantum mechanics in the mid-1920s. And in 1927, he wrote down an equation which described the relativist combination of relativity and quantum mechanics for the electron. And he discovered that although it worked very well for the electron, it also had a whole family of unwanted solutions that he didn't know what to do with. He struggled for 3 years trying to make the unwanted solutions have something to do with the proton, and it didn't work. Meanwhile, his friends thought he was a crank, and he was trying to do something which was impossible, and his equation was probably no good anyway. By the end of 1930, he reluctantly concluded that these solutions that he didn't want had something to do with what might be called an anti-electron, the first example of antimatter. And fortunately for Dirac, the anti-electron, now known as a positron, was discovered in cosmic rays in 1932, possibly a little earlier, but it was recognized first in 1932. So Paul Dirac waited only 2 years for the discovery. Another person who made a prediction was Wolfgang Pauli. He pointed out in 1931, looking at the process called beta decay, which Alan showed you in one of his pictures, where, for example, the neutron turns into a proton and an electron, and that was all that people saw, just the proton and the electron from the neutron decay. And the energies didn't add up, the angular momentum of the particles didn't add up. And conservation of energy and conservation of angular momentum were sacred principles for theorists. So Pauli said there must be an extra particle which hasn't been seen, and it was called the neutrino. The discovery of the neutrino had to wait 25 years. It didn't happen until 1956. And that was I think the second example of a theoretical invention being vindicated after some years. Let me go back briefly to Paul Dirac. My connection with Paul Dirac is that in wartime, 41-46, I attended the same secondary school in Bristol, where Paul Dirac had been a pupil a quarter of a century previously. And I think it was perhaps partly my curiosity about what he'd actually done, and he'd done a lot. He'd really written down the most general form of quantum theory. He'd predicted antimatter, and he'd written down the beginning of what we call quantum electrodynamics. I wondered what he'd done, and I think that perhaps led me to take an interest in elementary particle physics from a theoretical point of view. I also had the good luck to attend some lectures in Bristol University at the end of the war by Cecil Powell, who was one of the experimentalists who were involved in experiments setting up stacks of photographic emulsion with balloons up into the upper atmosphere, and that way, a year later, it was 46 when I attended his lectures, 47, he was the discoverer of the pi mesons, some new particles. Now, I decided I wanted to go in that direction in research. But after my bachelor's degree at King's College London, because theoretical particle physics looked pretty difficult, I settled for something a bit more straightforward for a PhD. My PhD was in molecular physics, otherwise known as theoretical chemistry. But in 1954, I moved to Edinburgh for the first time as a postdoc for a couple of years, because Nicholas Kemmer, who had been in Cambridge, moved to Edinburgh in '53 in succession to Max Born, and I had the opportunity to come and work with his group. I stayed here 2 years, and then to get my next grant, my next fellowship, I had to go back to London for 4 years. But finally, in 1960, I landed a real job, a lectureship in mathematical physics in Edinburgh, and I've been here ever since, apart from the odd sabbatical leave. Now, 1960 is a crucial year in the story of these discoveries that Alan's been talking about. It was the year of the first Scottish University summer school in physics in July 1960, just before I took up my lectureship. Amongst the students, there were four which I used to refer to as the gang of four, who stayed up halfway through the night discussing theoretical physics and never got up in time for the first lecture in the morning. Two of them later got shares of Nobel Prizes. One of them was Shelley Glashow, who was one of the authors of what's called the electroweak theory, and another one was T.D. Veltman, who was responsible, along with his graduate student Gerard Hooft in around 1971, for showing that the kind of theory which resulted from a combination of Shelley Glashow's theory of electroweak unification and the work of myself and 5 others in 1964, that this combination was a viable theory. In other words, in the jargon, it was renormalizable, that you could calculate with it just like quantum electrodynamics. So that was an interesting summer school. And though I didn't hear about Shelley's electroweak theory there, it was published, I think, the following year, I think some of the style in which he looked at theoretical problems perhaps rubbed off on me. He was keen on what used to be called model building, and that's not Lego. It's not real Lego. It's intellectual Lego. It's trying out quantum field theories to see if they will give you anything like the real world, and will they work? So I've already told you that the work which Glashow did, the electroweak theory, and the work that I and others did in '64 was later put together in 1967 by Stephen Weinberg and Abdus Salam to form the first stage of what's called the Standard Model. So I think maybe I should tell you a little about how over the years from 1960 to '64 I got involved in that sort of problem. I should remark at this point that in the early '60s there was no such thing as the Standard Model, so this is why what I'm talking about is in a sense prehistory from the current perspective. The language of quantum field theory, which was so successful in quantum electrodynamics, was very much out of fashion because of two problems which it failed to solve. One was the problem of the strong nuclear force, the way that nucleons, photons and neutrons interact with one another, And the other was the theory of the weak nuclear force. And really, if a theory doesn't do either of these things, it's doing pretty badly, so people gave it up. But it turned out in the subsequent decade or so that it wasn't the sort of general kind of theory which was wrong. People were applying it to the wrong thing. The strong nuclear force problem went away when it was discovered that really these particles called protons and neutrons, which we can actually produce individually and look at, are not elementary, they're made up of quarks. And that led to the solution of the strong force problem, actually not until the mid-70s, but before that, there was the solution for the weak force problem, which was associated, as Alan has mentioned, with the fact that the particles associated with the force field in the giving rise to weak interactions had to be massive, and a theory of particles with spin 1 and masses put into the theory just by hand, as if you've been told what they are, you plug them into the equations. That just doesn't work. So the route by which the weak force problem was solved was a bit roundabout. In 1961, I got interested in the work of a Japanese-born theorist, EUYSRA, who worked in Chicago, the University of Chicago, who was setting up quantum field theory models in particle physics, which worked by analogy with the theory of superconductivity. That may seem an odd thing to do, but the Bardeen-Cooper-Schrieffer theory of superconductors had been very successful, and Nambu by 1960 had spotted that there was a feature of that theory which might be put to work in particle physics. It's a feature which is called spontaneous symmetry breaking. It's very, very common in condensed matter systems because there are symmetries there which are ordinary geometric symmetries which nobody believes are really broken, but there are systems in condensed matter which appear to break them. For example, a ferromagnet, a permanent magnet, the basic dynamics has rotational invariance, like all the laws of physics seem to have. But a ferromagnet picks out a direction in space, and it looks as if you've broken rotational invariance. But the key to the apparent paradox is that what is breaking the symmetry is the most stable state, the lowest energy state of the system, the ground state in quantum mechanical language. The ground state breaks the symmetry because the electron spins line up all together in some direction, but it could be any direction. And once the ground state has broken the symmetry, then every other property of that ferromagnetic system looks asymmetric with respect to rotations. So Nambu thought that this trick might work for the rather more abstract symmetries of particle physics too. He was interested in models of the strong interactions. Everybody was at the time. People thought that that was the important thing to solve, and weak interactions were a sort of side issue for eccentrics like Glashow. But when Nambu wrote down some model theories to see how this would work, he found some interesting results. He found he could, by spontaneous symmetry breaking in a quantum field theory, he could generate the masses of elementary fermions. Now, fermions are the particles of spin half for example, which are the basic particles that make up matter. They obey the Pauli exclusion principle. So it was Nambu, and also in the UK, Geoffrey Goldstone in related work, who first showed that this spontaneous symmetry breaking idea could be used to generate from apparently zero masses of things like electrons, or at that time Nambu applied it to protons and neutrons because he didn't know any better. Quarks hadn't been discovered at that time. Now, that was sort of interesting, but it didn't impress people because there was really no theoretical problem about the electron mass or the mass of a fermion. People could use quantum electrodynamics just putting in the mass of the charged fermion by hand, and it didn't do any harm. It was the thing which did do harm was putting in a mass by hand for the force-carrying particles, the bosons, like the carriers of the weak force, or things similar to a photon but carrying different forces. So Nambu's work didn't attract very much attention, but it did attract some. It attracted mine, and it attracted the attention of Robert Bright, a condensed matter physicist in Brussels. Now, apart from the fact that generating fermion masses wasn't any big deal, there was a flaw in the theories of Nambu and Goldstone, because they predicted that some of the spin zero particles, the ones which don't have any spin, which are bosons, so-called the sociable kind of particle, always had zero mass. And that was a disaster because there weren't any such things known. So the discussion of that problem, which came to be called the Goldstone theorem, continued for a few years. And in 1964, 6 people altogether, including Robert Bright in Brussels and his collaborator Francois Anglais and myself, discovered how to cure this difficulty. My own part in it was that I realized that the theorem which had been spin zero particles without mass in these models was based on axioms which didn't include the possibility of so-called gauge theories, that is, theories of the type of Maxwell electrodynamics. And once I spotted that, I wrote a short note which got published saying there's a way out of the Goldstone theorem, bring back Maxwell, he's the cure for all our difficulties, as it were. That got published. Then I wrote down the simplest example I could think of, showing how it actually worked, and that showed that what happened was that the unwanted spin zero particles disappeared, and instead you got an extra polarization of the spin 1 particles, which is just what you wanted for a massive spin 1 particle. And that's what is known as the well, sometimes it's the Higgs mechanism, or more correctly, the Bright-Anglais, Higgs, Uranic, Hagen, and Kibble mechanism. In other words, what the 6 of us did then is nothing to do with the generation of mass for ordinary matter. It's the generation of mass for the particles or the quanta associated with the transmission of the forces. And when I sent off my note giving a very simple model for publication, it got rejected, and I couldn't understand at that point why they wanted to publish the first paper. And in the course of revising it and sending it across the Atlantic to a different journal, I added some comments which indicated that there was some experimental consequences of using this kind of theory, which would be different from any other type of theory. And in particular, I pointed out that there's always at least one leftover massive spin zero particle in the in theories of this type, and this is what became known as the Higgs boson. And it was a very sort of minor point at the time, but as the years went by and the electroweak theory of Weinberg, Salam, Glashow turned out to be more and more successful and also viable in terms of theoretical calculations, attention gradually turned to this odd feature, which is not something not new to the so-called spontaneously broken gauge theories. This leftover massive particle was already there in what Nambu did, and indeed if you go back to the theory of superconductivity, you find that there are excitations in superconductors which have this property too. So it's nothing new, it's just that I drew attention to the fact that this model, which has become successful in particle physics, had to have this feature too, and thanks to the efforts of John Ellis and people at CERN drawing the attention of experimentalists to the prediction over a period of, well, since John Ellis's work in 1976, it's 36 years, gradually the experimental programs have turned their attention to finding it, and it seems to have been discovered at last. I mean, my own position has always been, well, you have to have it, because if you take it out of the theory, which you can on paper, as it were, the theory just goes wrong, you get nonsense. So from a theoretician's point of view, it was a good bet. Now it seems to be part of reality. Thank you.
Well, Peter told you his part in all of this. Just to finish off where we are with this, Peter's model was of a simple model which actually ended up with one leftover massive scalar and one massive vector particle, that being essentially a heavy photon in the sense that it was actually didn't have enough particles in there for what is to come in terms of electroweak. So I just want to take you a little bit through that. In electroweak unification, we need to actually have the W's, which there are three of, and the Z, which are three particles. These, if we start off with massless gauge bosons, then it turns out that in order to make the theory work, we have to introduce not just one Higgs field, but four embryonic fields. And if we actually do the combination, then after we've actually made them massive, we have 3 plus 3 plus 3, that's the WZ and the and this. But if we actually go back to where we start, if we actually have massless gauge bosons, these only have 2 degrees of freedom, so that's 2 plus 2 plus 2 plus the photon, which is 8. So we have to introduce 4 Higgs bosons, which have 1 degree of freedom, so that's 12. But when we actually do the game afterwards, the W's become massive, they have 3 degrees of freedom each, which is 9. We have 2 degrees of freedom for the photon, which stays massless. And here we have it, the Higgs boson left over. So in terms of counting the number of degrees of freedom in the theory where we start off with the massless particles, the W plus, W minus and Z are massless, and we have the photon which remains massless, we have to introduce 4 Higgs, and that fourth Higgs field becomes the Higgs boson. So I'm not going to go through this because I think time is moving on. What we actually should do is actually now look with Victoria at about the LHC and Atlas, and so I'm now going to hand over to Victoria.
So Alan and Peter have told you the theory behind this particle, the Higgs boson, and I want to tell you how we go about looking for it and finding it and see if it really exists or if it's just a really nice theoretical construction. So I came up with a little recipe here if you'd like to try this at home this evening. So firstly, you just take two very high energy protons. Now the ones I use are fresh from CERN, but any ones that you have around are fine. You smash them together, and then if you do this 10 to the 10 times, 1 in 10 to the 10 of these collisions will form a Higgs boson, at least that's the theory. And once it's formed, the Higgs boson will decay after about 10 to the minus 22 seconds. So you don't have very long to work out if you actually had one or not. But that's fine, because what you can do, and what I did, was assemble a highly sophisticated state-of-the-art detector around the collision point where I collided my two protons. And then what I did, instead of looking directly for the Higgs boson, is I observed the particles that were produced when the Higgs boson decayed 10 to the minus 22 seconds later. And then you just repeat this 25,000 times a second for about 1.5 years. And maybe you too will see a Higgs boson. But I want to break this down and tell you a bit more about how we actually do it. So, this is CERN. CERN is the European Organization for Nuclear Physics, which somehow abbreviates to CERN. That's what we call it nowadays. It's located near Geneva. It's actually on the Franco-Swiss border. And CERN itself is a collaboration of 20 European countries, including the UK. It has about 4,000 employees, but more important than that, it has about 10,000 visiting scientists, of which I and Francisca are one. And they come from 608 universities and research facilities throughout the world, of course including the University of Edinburgh. And what does CERN do? Well, it provides the particle accelerators that are used by 17 different experiments that are at CERN. So this is just if you're driving past, you see this little sign, and they've now built this kind of iconic globe. So this is now what I think of as CERN, and you can see it's out in a nice countryside. That's the nicest part of CERN. Not the most exciting, just the most obviously beautiful. So what we use to produce and look for the Higgs boson is the Large Hadron Collider, or the LHC. So this is currently CERN's main activities, but it does do other experiments. The Large Hadron Collider is just the end of a chain of accelerators, and this chain of accelerators are not new. They've been built up over decades, over the past probably 60 years now, and the one thing that's really good at the LHC is they've reused a lot of the facilities that they had built for previous experiments. And what it does, the LHC itself, is accelerates protons to an energy of what we call 4 tera-electron volts. Now, if you're a physicist, or even if you're if you're not a physicist, or even if you are a physicist, you might quite know what that energy is. I'll tell you, it's the highest ever energy for an accelerator. It's 4 times bigger than the previous accelerator, which was in the States. But you really need those really, really high energies to look for the Higgs boson, because, as we found out, it's very heavy. And currently the LHC is running. We're going to spend next year upgrading it, and after 2014 or 2015, we hope it's going to run at even higher energies, double what it's running at now. So I just put this little diagram in of all the different accelerators that are used, and the final one is the LHC. I've got a video afterwards, and then these are just the energies that each thing starts as. How do you get the protons to begin with? This is the source of the protons for the LHC. Can anyone guess what it is? It's a bottle of hydrogen. Protons are quite easy to get. Or you want to try this at home. So a bit more about the LHC, because it's really a fascinating machine. And I'm an experimental physicist. I didn't build or think about any of this. It's really the great scientists at CERN that do the accelerator physics that bring us this facility for me, one of the scientific users of CERN, to use. So the Large Hadron Collider is, I do have some facts coming up, is 27 kilometers around, and here you can see it projected onto a picture just outside Geneva. At the top of the red circle, maybe you can just make out that's the runway of Geneva Airport. EasyJet fly, if you ever want to go and visit. This is a very old picture from the 1980s when they were actually digging the tunnel. So the LHC is between 50 and 125 meters underground, depending on how steep the land is. And so they dug a tunnel specifically not for the LHC, but for one of the previous colliders they had at CERN. The LHC itself, what it has to do is to keep the protons, which are very energetic, going round and round and round and round. And it does that mainly by using magnets. So this is one of the dipole magnets that's used in the LHC. And how you actually keep the protons going is inside that magnet there's two beam pipes. So you have one set of protons going this way, and another set of protons going this way. And they go round and round for 27 kilometers. Round and round, hopefully now my figures will come up. What did I forget to tell you? There's almost 10,000 magnets in total. The main workhorses are these blue ones, which are shown here, these dipole magnets, which there's over 1,000. They all cost $500,000 Swiss francs each. They've got a very high magnetic field, and they're almost in the best vacuum you can make. I think I remember it's actually the best vacuum in the solar system is inside these beam pipes at the Large Hadron Collider. Why? Because you've got protons in there and you don't want them bumping into air molecules as they're going around. You want them in a vacuum so we can control them. So basically the LHC is the ultimate atom smasher. We don't just take one proton out of that hydrogen bottle and one proton and smash them into each other. That's not very efficient. What we actually do is take 10 to the 11 protons going one way around the tube, 10 to the other way around the tube, and then 25,000 times a second, we collide them together. We smash them together at 4 different points around the LHC circle, which is now hidden behind there. And out of that, we want to find the Higgs. So, sorry, this is a very scientific plot, but it was the best one to illustrate what I want to say. Basically, 1 in 10 to the 10 collisions, like I said, will make a Higgs boson. And this plot shows you why that is. Basically, the line at the top. Yes. So I collide 10 to the 11 protons with 10 to the 11 protons. This is as a function of the collision energy. But basically, up here, this is where something happens. Anything. And this is a logarithmic plot. So if I go down and look for what I'm looking for, so this is me making a Higgs boson there. So 10 to the 10 times smaller, I can make a Higgs boson. So it's a bit of a challenge to find a Higgs boson because you have to make all those collisions, you have to collect and analyze all the data just to look for that needle in a haystack. And it's not even one needle in a haystack. Someone said it's one needle in 25,000 haystacks traveling nearly at the speed of light. So it's rather a challenge. But the good news is the Higgs decays, but we know what it decays into, and these are the predictions of what it decays into. So basically what we do is go through that huge amount of data we're going to collect from those billions of collisions and look for these pairs of particles that the Higgs boson has decayed into. How do we do that? Well, the LHC brings us the protons. How do we detect the particles that were created when the Higgs decay? Well, we use this. So this is what I use. This is the Atlas detector. I'm sure most of you have seen this picture before. So that's actually before the detector was put in. So actually all of this area now is filled up with more detecting equipment. this is the artist's illustration. It is not in these pretty colours. It looks a bit more like this. So this is actually them putting together the last pieces of the detector. So they filled in the bit there where we saw the man standing, and they're putting it all together. Here. I thought I'd show you a bit more what it looks like in real life. It's not great resolution, but this has been building it. It took 3 years. This is an illustration now of, firstly what they're doing is they're speeding up the protons in that network of accelerators that we saw, and they're getting faster and faster as they go through, but you can see the scale of these things. So you can see that there's 2 protons, one going one way and one going the other, but remember there's actually 10 to the 11 and 10 to the 11. So this is now inside the LHC beam tunnel with a bit of graffiti, and these are these dipole magnets that I was talking about. You can see each time they go around, they go past the French-Swiss border. This is a proton with the 3 quarks inside it, still accelerating, and it's just about to meet a proton on the other side. Smash. And what comes out basically is just like that, it's just fireworks. So we know we put the 2 protons in, and we can see all of the particles that came out. Actually, the detective work is trying to work out what happened in the middle. So we see the beginning and we see the end, but what happened in the middle was what happened in the middle of the Higgs boson. That's what we're trying to work out. And that's what we actually spend most of our time.
Is there a cloud of these going through, or is it warming and light?
No, it's like little clouds. So there's, I think at some point the shape, the kind of the size of a grain of rice. So there's 10 to the 11 protons, and every 25, well at the moment every 50 nanoseconds, another of these, we call them bunches of protons, comes through, and then they collide one at a time.
Why I was asking, the picture you see presumably is of tens of thousands of these all at once.
Actually, we have 10 to the 11 and 10 to the 11, and it turns out that because protons are really, really, really tiny, it's, sorry, I'm trying to...
Normally there's 1,232 bunches in each circuit going around 11,000 times per second, and in each bunch there's 10 to 11. And then one or more proton will collide in any bunch.
So you do see an individual event.
Yeah. But the magnificent thing about what they do is that they can actually disentangle 20 events at the same time.
Yeah, so that's...
Up to 20.
There's up to what, 35 we've seen now, so up to 35 individual interactions.
The near the limit that we can disentangle.
We can disentangle them basically because
Not
most of them are really
10 to 11.
uninteresting. Right. So we've seen my detector. It's called the Atlas detector, and basically it's the largest and most sophisticated digital camera ever built. I mean, you saw it in the video. You saw the gentleman there. It's 45 meters long, 25 meters in diameter. I looked up what it was compared to a building in Edinburgh, and it's kind of the size of the McEwen Hall. I mean, it's enormous, and it's 7,000 tons. However, 7,000 tons for something that size makes it lighter than water, so it would float if you stuck it in a Ziploc bag. Right, so how do we use this to look for the Higgs boson? So we think we know what the Higgs boson might decay into. So it might decay into what we call photons, and which Alan mentioned before, which are particles of light And actually, this is one picture that we've taken of a real proton-proton collision, where what we see are, so you can see the fireworks, but the important things you can't see very well in the light are these yellow blobs here and here. And these are from photons. And this is another projection of them, because it's a three-dimensional camera. These are the two photons, sorry. And that's kind of what we'd expect to see if we saw a Higgs boson. But one's not enough. Here's something else. This is actually what Francisca works on for her PhD. Here with the Higgs boson can decay into Z bosons. Now the thing about Z bosons is, as they actually decay too, they decay even quicker than the Higgs boson. So what we don't look for is these, but we look for what the Z decays into. So it can decay into electrons, this E minus or E plus of these positrons, these anti-electrons. And here is one picture where we see, among the fireworks, but these are actually the dominant things. I think it's even easy to quite see in this. The dominant things are these 4 electrons here. And this again is another projection. So like I've said, the challenge is that only 1 in 10 to the 10 might be the Higgs. We've got the other 99,999,999, that is enough nines, times where something else could happen. And something, because that's very often, it could end up looking the same. And actually what we need to work out, if we see this, was that the Higgs or was it something else? And you can't actually do that. You need to see it a lot of times, and you can work out probabilistically, was that the Higgs or was it something else or was it both? This is just another illustration because I quite like this one of protons colliding, and this time again we see, instead of the Z boson decaying into electrons, we see them decaying into positive and negative muons. So we've collided the protons together, so we just repeat this 25,000 times a second for 1.5 years. So this is looking for all of the collisions where we find 2 photons, like I showed you in the first picture there, and then we work out what the mass of those 2 photons comes from. So you can see there's a kind of falling distribution. Now that's just, the hypothesis is at least, that's just what happens because 9999999 in 10 to the 10 events, you don't get a Higgs boson, you just get something random. But here you can see there's a little bump. And actually what they've done there is taken the red line off the bump to make it a bit more convincing. You can really see there's a bump. So there's a small, what we call excess of events, that's what we call it, at this particular mass. So just this mass, we call it 1 GeV, is about the mass of a single proton. So at about 125 times the proton mass, we see a little bump. And we believe that this is due to the fact that in all those collisions, 1 in 10 to the 10 times we're making a Higgs boson with a mass of 125. And just to show you the same thing for the Higgs to ZZ, these little bumps here, these are the data we've taken, it's a histogram, and you can see that they are consistent with the fact also that we see something in the data that looks like 125 GeV Higgs boson. Right, so I just wanted to leave it there. Francisca is going to tell you what it's actually like to work on this and come to a few more conclusions about what we're seeing there in the data.
Just before Francesca starts, probably it's not beyond your notice, it turns out that Peter and I taught Victoria, and Victoria is now teaching Francesca, so you're actually witnessing a 3-generation event here. Francesca.
Okay. Hi, so I was asked to tell my story as a PhD student, how my experience has been. I'm on 2nd year now. So my super imaginative title is A Story from a PhD Student. First I want to talk about where I come from. So as you can see on my accent, I'm from Chile, so I started to working on Atlas from there on my master's degree. And in Chile we have 2 universities and approximately 15 scientists in the whole country that are working on Atlas. So when I started to think about my PhD, I was okay, I need to go somewhere near Atlas and CERN to be a better scientist. So I applied to Edinburgh and I was accepted, so yay. And then I took a really nice flight of 15 hours approximately, and I traveled 12,000 kilometers. I really recommend that trip. And then I got to Edinburgh, and I found that only in Edinburgh we have 20 scientists and 6 different nationalities working all together and collaborating with each other. And also, on my first year, I get to travel a lot, to go to conferences, to show what I've done, workshops, and also traveling a lot to CERN at Geneva, at Atlas. And when I got there the first time, I realized that that's wrong. It's not at CERN, it's at Atlas Collaboration. I found that there were 3,000 scientists working together, 38 nationalities, and 175 different institutions. The good thing is that they can work together and they make things work. So here I show you a picture of the Atlas collaboration. So you can see that almost half of the building is filled with people. Yeah, so this was just to show you how big this collaboration is and how global is it. I mean, also in Chile we try to do something for it. So what does the Atlas Particle Physics Experiment Group does in Edinburgh? So mainly we do Higgs searches, so we divided in 2 groups more or less. So Victoria told you about the Higgs decay into a pair of Z bosons, and then these Z bosons can decay to 4 leptons, and that is one of the searches. I'm particularly working on it. And the other search is the Higgs decay into bottom-antibottom, and that is the analysis parts. The other thing that we contribute is on the Atlas simulation. So we need to somehow know how the detector works, and we need something to compare with the data that we have. So we basically simulate events, we simulate the pass of a particle through the detector, so the particle, how it behaves on a certain material. And then also we collaborate with the Atlas upgrade. On December it's going to be a shutdown for 2 years, I think so. And all of this to make the detector better, and we are also making some contribution there. The other picture are the ones that we are based at Edinburgh here, and the other pictures are the ones that are based at CERN in Geneva. So yeah, we have a big announcement on the 4th of July. So I want to show you some pictures to show you how was the excitement on that day. So we have that picture is the theater where the CMS and Atlas talks were. And then these other 2 pictures, there are people waiting online to get a seat on the lecture that day. I even have a friend that was doing the line and spent over the night to get a seat on the lecture. And personally, in my case, I was visiting my parents in Chile, and I woke up at 4 a.m. in the morning to see Korean Air or whatever, but I'm proud of it. So, what was this big announcement? So basically, there was announced the observation of a new particle, and this was after the announcement, so everybody was happy. And then we have Professor Higgs there. Yeah, so this is the difficult part. How do we interpret the results? the result from it, we usually end up seeing these kinds of plots. They talk about the p-values, they talk about we have a discovery for 5 sigma, blah, blah, blah. And I also have an extract from the actual paper, and I'm going to read some of the lines. So it says, clear evidence for the production of a neutral boson with a measured mass of 126 GeV is presented. This observation, which has a significance of 5.9 standard deviations corresponding to a background fluctuation probability of whatever 10 to the minus 9, is compatible with the production and decay of the standard model Higgs boson. Did you understand something? Me neither. But the point is that I want you to remember that we are 99.999995% sure that we find something, and the mass of that thing that we find is around 126 GeV. And this is what these plots try to interpret. And some final words. So in my experience studying physics, I've always heard these stories about people far, far away from my continent even, that did this, that discovered this, that they changed history. And just to name a few, I have like a timeline. So I have James Maxwell with the electromagnetic waves in 1862. Then we have Marie Curie for the discovery of relativity. Then Einstein for the theorization of photoelectric effect. Then we have Professor Higgs on 64 for the Higgs particle. Then we have Rubia and Vandermeer for the discovery of the Z and W boson. And now we have the discovery of the Higgs, the experimental discovery of the Higgs. Now we are really honored with being part of and having a small role on this story. And yeah, that's what I wanted to tell you, that I'm really glad that I could be part of it, and I'm part of it now at present. So that's it, thank you.
Spokesperson of the Atlas experiment who spoke at the July the 4th seminar is Fabiola Gianotti, and she has kindly sent a present which I'll ask Francesca on behalf of Atlas to give to Peter. Just to let you into the secret, Peter now has 2 t-shirts with that plot on it. Inside, there's a special edition of the 2 papers from Atlas and CMS, which is actually signed with gratitude to you, Peter, from Fabio. Okay. Thank you.
Alright guys, the event is called An Audience with Peter Higgs, so we'll be having wandering microphones, so if you have any questions, then please raise your hand and wait for a microphone to come on. So the first question would be down here. Yeah, hello. Is it on?
It's on. Professor Higgs, I just really want to know, first of all, what it's been like for you with all the publicity surrounding the Higgs boson, and after the announcement at CERN in July.
Well, the problem started the previous July. I mean, it was July 2011 that there was the first hint of something around 125 or something. Yeah. And I mean, I started getting requests for interviews even back then. It just got worse and worse over the following 2 periods of 6 months, because by December 2011, December the 13th, was the next announcement, significant announcement from the LHC teams. And that was the occasion when I got a message from the Director General, Rolf Hoyer, saying, well, it's not going to be a discovery claim, but we'll have it settled by the end of 2012. So I was sort of prepared for things to happen and become definite in 2012. What surprised me was that they settled as much as they have settled as early as July 2012. I fully expected it was going to take a lot longer to do the analysis, but in fact it went extremely fast and extremely smoothly, as far as I can gather.
Next question.
No, I think actually that I can actually give some impression of what's been going on with a few slides. Just to show you how this has been going on for some time, this is someone who sent us a CD eventually, who changed his name by default to Higgs boson. He's a jazz guitarist from Cornwall, I believe, but I'm told by Peter's son he's not a very good jazz guitarist. This is a Higgs boson, it says on there, but in fact I'm not technically competent to comment, but it's actually known as a grind wheel for your inline skates. I think this is how you go down round railings. That's been on sale for some time, and this came from a shop in Cumbria. Charles James, whose wife Maggie is known for the Maggie Centres, who sadly died of cancer, has a garden in Dumfriesshire where he has dedicated to science. It's called the Garden of Cosmic Speculation, and if you look carefully it says the Standard Model, and in there's the Higgs, so it already has a burial place, it looks like. You get fluffy toys called the Higgs boson. I'm told that Peter already has two, and that was well before July the 4th. There are two racehorses called Higgs boson. One is a novice hurdler that comes from Ireland. It's running 2 races a day, and it's come second twice. But when I tell you that he was in a field of 2 and then a field of 3, it's not really successful. The one you see here is a thoroughbred raised in, I think, Australia, but runs in Singapore, and it's already earned at least 118,000 Singaporean Swiss dollars. So you could bet on that one, so you could actually bet on that one. I look after Peter's email, and as he said, he doesn't use a computer. I received it at a Tai Chi class, he fell to 5th course, and encouraged him to find the Higgs boson. It even appears in the Sunday Times crossword if you can do anagrams. And after July the 4th, we actually got inundated with requests for things. Peter is actually born in Newcastle. Some people think he was born in Wallsend, because that's what Wikipedia says, but he was born in Ellswick. But this is Red Watch Station Kilo, collects pictures for their wall of Tyneside celebrities like Ant and Dec and Alan Shearer. Well, in that illustrious company now Peter sits with pictures on the wall. We received a message from someone in Netherlands who'd actually decided they want to name their new boat something, so they call it Higgs. One of the common spelling mistakes or deliberate mistakes about the Higgs boson is it's sometimes called the Higgs boson. And so presumably there may be one on board that. And we're involved with a small brewery in Barcelona. Peter and I are going to Barcelona next week, not specifically for the beer, but I think we hope that it will be finalised by then. It's in the bottles being finished apparently, and I'm collaborating over the production of the label. And then finally, Peter hasn't even heard this one yet. This came on October the 5th, and I have the mail for him with pictures. And some family in Holland decided to name, to actually have 2 cats, and the son wanted one called Higgs and another one called Boson. And then they said, well, of course, if we're actually calling them in of an evening, it'll be Higgs Boson, where are you? So there you are. That's just a sample of the things that have actually been going on in science in this area. I think we should have another question.
All right. What was the next question?
I'm asking this question on behalf of my professor who got his PhD from the University of Chicago. He was very interested at how Peter Higgs and other theoretical scientists that have the insights of Einstein in predicting the theoretical foundations of physics long before experimental activities have taken place. So how do you relate to many voters' interpretations, or maybe it's just a crude model, or based on your work on Higgs mechanism and symmetry breaking and its relations to the uncertainty principle? Do you accept the what is your take of Copenhagen's interpretations of quantum physics? Is there like
well, I don't know about inspiration. I mean, what enabled me to arrive at the kind of theory which is built into the successful electroweak theory was simply the realization that two things that I already knew had to be put together. I mean, it was as simple as that. And I mean, there's a lot of background which I didn't have time to explain, where there are a number of papers in the previous year or so, one of them by the condensed matter theorist Phil Anderson, another by Julian Schwinger, which were sort of hinting at what was needed. Anderson himself speculated that it had to work the way that it does work because something similar happens in a superconductor. But the problem was he did it in a language which didn't confront the constraints of relativity theory, which were used in the formal proof of what was called the Goldstone theorem. And there's a missing piece in the story, there's a paper which nobody, as far as I know, has yet written, which would explain why it is that if you want to have a relativistic theory involving long-range forces of the type of the Coulomb repulsion, an inverse square law force 1 upon r potential, then you have to have a gauge theory of the maximum type. I mean, that's the connection, which was, I mean, I did it in one language, which is appropriate for relativistic field theory, but Anderson had sort of speculated that that was going to happen anyway because of what he knew about the non-relativistic dynamics. As for the Copenhagen interpretation, I think that's too long for a meeting of this kind for me to answer.
So once we confirm existence of Higgs boson, what else do we need to complete the standard model?
Well, in one sense, the standard model is complete. At least it's sort of over a certain range of phenomena. I mean, what it was supposed to do is, as I think pretty well for the most part being verified, but there are simply loose ends which tell you that it's not enough. I mean, there are the properties of neutrinos is an outstanding example. The Glashow electroweak theory started in around 1960 from the point of view that the so-called leptons that we know that in weak interactions is the electron which has two spin states, one way and the other way, and the neutrino, which apparently was massless and had just one. And what Glashow did was to use a symmetry scheme which has been pointed out as relevant to these weak interactions by Yang and Lee just before he did the work, and write down a kind of gauge theory, but with mass terms put in by hand, which fitted that symmetry and which used no more than the particles of the lepton family, that lepton family which were known at the time. Subsequently, it turned out that neutrinos are much more complex than people realised, that there are very small neutrino masses somewhere amongst the set of them, and therefore the standard model has to be extended. It's pretty good in what it does, but it doesn't do everything, and one of the big mysteries is the way in which these neutrino masses come about. That's for the next generation of theories.
Some of us in the audience here are not physicists, and me and my little friend here are wondering whether you have a simpler way to explain the Higgs boson for us.
We need a chair on the stage. So what's your name?
My name is Sida.
Sida Guerrero. Yeah. Sida. So this is Sida. What I want you to do is, with your father's permission, to stand on this chair. Not. And face me. Okay. Now, I want you to look at these. Do you think they're any different? Just feel them. Do you feel any difference between them?
Well, yes.
What do you feel?
This is painted, this is sellotape.
Well, apart from the sellotape, they feel much the same, okay? Right. I want you to look through the tubes and tell me if there's anything in them. Are they clear?
There's something weird.
Yes. But is there
yes.
light at the end of the tunnel?
Yes, it's not totally.
Yes, of course, right. Okay. You want to hold them and feel if they feel different? Differently? They feel the same. Okay. Now I have a question for you. If you were to drop these together, if you drop them simultaneously at the same time to the floor, will they arrive at the same time?
Yes.
Yes. You're doing well here, right? Okay. So we assume that that will be the case. Okay. Now, if I was to drop them down these empty tubes together at the same time, will they reach the floor at the same time? Yes. Okay. Well, we have to do experiments. You hold on to that and hold on to that. Now, hold it by the end. Okay. No, this end. Okay. So that they're actually going to be put into this tube. So, 1, 2, 3. It got stuck in the other tube, didn't it? Congratulations, you're actually right. Thank you. Can we have a round of applause? Indeed, one of these is a magnetic slug and one's non-magnetic, and these are two metal tubes, but the tubes are non-magnetic, so the magnet does not stick to the tube. Okay. Does that look like a circle to you? See that? The end, this cross-section looks like a circle. So we've got essentially a joined-up piece of wire all the way down. So when the magnet goes through it, it generates an electric current, which generates a magnetic field, which pushes back on the magnet and slows it down. So it accelerates them to the point where the force pushing up is the same as the force down, and it drops at a terminal velocity. But the one that's not magnetic doesn't actually interact with the metal, and it reaches the ground just still accelerating. So what really is happening here in the analog with the Higgs field is the fact that the magnetic slug actually interacts with its environment, or its environment interacts with the slug, whereas the non-magnetic one doesn't interact. Now, if we actually imagine the Higgs field is all through space, then the particle which has mass interacts with the Higgs field and interacts with its environment, whereas the massless particle doesn't. And the interaction with the environment will depend on how massive the particle is, or the Higgs fields interact with the particle, therefore to endow it with mass. So we have to imagine that all the space is endowed with this Higgs field, and that the interaction with this environment of the Higgs field is what leads to the particle's mass. However, this is only analogy. This is actually works on classical electromagnetism. You can solve this problem from Maxwell's equations. What Peter has introduced is an entirely new field and an environment that you don't see, the Higgs field, in which these particles achieve mass. And it's not everything that gets mass. That's another common mistake that's said in the popular literature. Everything gets its mass from the Higgs field. Only those elementary particles, the quarks, the leptons, and presumably the neutrinos, get their mass from interaction with the Higgs field, and also the gauge bosons, the W's and the Z's, which actually are massive. So thank you again, see that. Okay.
Second last question, then we'll have one more question over here.
Professor Higgs, you see the press constantly call the Higgs boson the God particle. Do you like that name?
Well, I mean, what I said about that was that, well, I mean, this goes back to, well, there was a time in the early 70s where after a conference at Fermilab, when my name had been attached to everything in this kind of theory, and some of the other people were understandably displeased about it, and of course they were relegated to a footnote. So my reaction is to your question is that well, keeping my name on the Higgs boson amounts to sort of acknowledging that I made a point of referring to it when the others didn't. But then, if you ask, say, Francois Onlaire why he didn't refer to it, he and Robert Brout, they say, well, it's obvious. There was no need to. There was a need for me to refer to it because the first version of my paper had been rejected. So I had to put some extra things in to say what was special about this kind of theory. So, I don't know, is that a satisfactory answer?
The question, Peter, was about the God particle.
Oh, the God particle, sorry.
That's the second.
Oh, well, that I object to extremely strongly.
This is a question for the whole panel, and it's about the application to this discovery. Do you think that it just purely bolsters our theoretical models, or do you think there's any technologies that we can look forward to as a future that will derive from the discovery of the Higgs boson?
I have no idea what uses is. I suspect none is the answer. But why should you expect me to know?
I agree with Peter.
Me too.
I'd like to say one thing. Richard Wilson, who was actually the first director, or the person who had to set up Fermilab in the States, was asked a question. He was asked a question by a congressman who said, and tell me, Professor Wilson, what will this do for the defense of the United States? And the answer was, well, like art, poetry, music, and the other fine cultural things in life, essentially it will do nothing for the defense of the country, but it will make it worth defending. One of the things that you should be impressed with which is about what the experiments have to do in order to actually find the Higgs boson, is that they have to push the technologies and the physical frontiers of those technologies enormously. Superconducting magnets are now routine in hospitals for MRI scans, but they weren't invented for hospitals, they were invented at CERN for producing these high magnetic fields. But that's one example. I should remind you that the World Wide Web was invented in CERN, just as a way of actually transferring information between institutions and collaborations and so on. And good or bad, the World Wide Web is here with us, and there are people probably in the audience who don't remember the day when they didn't have it. But essentially, the technology that's pushed in this sort of thing actually does itself, in order to find the Higgs boson, mean that there will be applications of those things. But it's very hard to say that this will be immediately. One other thing I should say is that J.J. Thomson, who discovered the electron, wrote on the walls of the Cavendish laboratory in Cambridge, "God bless the electron, may it be of some use." I think that's enough to answer your question.
Thank you very much to the entire King's panel for coming along this evening. Just so everyone is aware, this isn't the last meeting of the semester. We still have two more where we have Dr. Richard Hill coming in talking about science in the age of disinformation. That's the 13th of November. And then we have Professor Setsu Kumar, who's going to come in and talk about robots that learn, altering new tools. But just in case you didn't know, Vijay Kumar's robots came third in the Robot World Cup. So definitely a man to come along and he'll have gadgets as well. And then to finish off, we have a couple more things. Fundraiser, I didn't mention this before, but we have a K-League scheduled for the 18th of November, and we're going to be selling tickets outside by the entrance of the doors. So £8 for one person, £15 for two people, and £20 for 4 people. So please, it's for charity, it's for research in prostate and breast cancer respectively. So please come along to that, it'll be a great evening. And then I mentioned it earlier, the Christmas dinner. At the front we'll be taking new memberships and also registration to the event. Finally, Principia Scientifica is going to take 4 minutes. Each side gets 2 minutes to argue their side of the topic. And today it is, can scientific theory be considered undeniably true? And first we have David Pepperly to argue, what is it?
It can't be proved true, actually.
It can.
Right, so Nick came to me last week and said this was the question, and I said yes, science theory can be proved undeniably true. And I went home and thought about it and realised actually that was a terrible idea because it can't. But anyway, I'm not going to think about it. So can it be proved undeniably true? And there is a situation where it could be, and it's hypothetical, so bear with me. If we were omniscient beings and we knew everything, then of course we'd be able to prove things undeniably true because we would know everything, and that'd be fine. If we're omnipotent, we could make it true. That'd make it much easier. And this is a scenario where science theory could actually be proved undeniably true. This is great. I'd also thought I'd take some current theories and say why they're always true. And the first one I'll start with is gravity. Gravity always wins. So if on an evening I decide to have a few too many beverages, later that evening, inevitably, I will end up closer. This isn't just dependent on alcohol, penguins also suffer the same fault. The next one I thought I'd talk about is mental inheritance. So this is sexual reproduction. So yes, if two parents have a child, that child will share the phenotype of the parents. So if Simba and Mrs. Simba decide for a baby, but the postman is Tony the Tiger, and the child comes out looking like a tiny cute tiger cub, then Simba has every right to be annoyed. This is always true, both to share phenotype and the fact that your partner will be pissed off if you're cheating. And the last two I'll talk about, one is the one of the laws of thermodynamics, and that is a closed system will end up at thermal equilibrium. So if we take students in Edinburgh, for instance, that come home from the library, then that will be at 25 degrees, and they get back to their flat in Marchmont, which is just above absolute zero. Within 5 minutes, they will also be just above absolute zero. That's also true. And the most important one, as we've seen a little bit tonight, is Sod's law. If something can go wrong, it will go wrong. Toast will fall butter side down, your presentation will have some hiccups, that kind of thing. So this is always true. And I'd like to finish as Okay, well, I had a quote from Carl Sagan, who's a popular scientist who made science quite cool. That was in 1970, kind of Peter Higgs kind of time. And he said that the science method isn't perfect, but it's the best we have, and skepticism is the future, and without it, we'd be in the dark age. So, although science theory may not be able to be proved undeniably true, it's very important, and actually there are some occasions when it does turn out to be true all the time. Thank you very much for listening.